This podcast is brought to you by LMU Munich.
Okay, good morning everybody, and I thank the organizer for this nice event, and I hope that we all will make it really as enthusiastic occasion to discuss about the rapid development that we have been witnessing in the last, let's say, 6-7 years, and about the new calculation techniques for computing scattering amplitudes, but also about a new understanding probably of the properties of quantum field theories. So I have titled my lecture Basic Structure of Scattering Amplitudes because at the beginning of these, so for the first 3 hours, I'd like to settle down the notation, hopefully common notation among the 4 speakers of this school, and try to get the contact between the notation that you might find in a usual textbook and a more compact notation that we will be using. And for the rest, so the second 3 hours, I will discuss more of about advanced topics. So today I will stay at 3 level, and then we move 1 loop higher day by day. So just 1 loop per day, like the apple keeps the doctor away. So the reference material that I'm using for this introductory lecture is listed here, and I try to alternate a Blackboard talk calculation, mainly QED based, with some more lengthy formula for QCD that I will show on the slide. So you don't need to take notes about the slide because they are available to you, and eventually just take notes of what will be on the Blackboard. Okay, and if there are questions at any time, you can just interrupt me. So when we think of particle scattering at Hadron Collider, for instance, okay, we start with proton. Let me switch. Okay, incoming proton, then we have some of its component colliding with other particle. Okay. The collision is usually kind of quite involved process to describe completely. Some basic representation can be sketched in this way. So from really the beam in the accelerator machine till the observed particle, we could divide the whole process in technically 4 phases. There is an initial part ruled by the parton distribution function, which describes the probability that some parton can generate what is the hard scattering. Then there is a phase where particle shower, and then there is a last phase the hadronization and decay, where particles recombine together to get to be observed on our experimental site. And this dashed line here are a very sketchy parameterization of our ignorance. Okay, we can describe the evolution, let's say, of the particle production according to the energy involved, okay? And what I will be concentrating on for the rest of my lectures, and probably also for the rest of the workshop, will be something related to this phase, okay? In particular to describe the interaction, the base interaction among the partonic element of the collision. So the basic quantity that we all learn during our quantum field theory course that describe the probability of an event to take place is the cross-section, okay? And these formula should be known to all of you. So the cross-section contains three types of building blocks, namely a flux factor, then an integration over the phase space, and what we have here is the amplitude square summed over spin and averaged over spin, let's say, of the incoming particles. So this is the first place when the scattering amplitudes entered the game of quantum field theory. And in particular, scattering amplitudes as the picture of Feynman diagram of Feynman remembers us there at the beginning of the door. So the scattering amplitudes can be obtained by the sum over diagram, so over Feynman graph of incoming of the Feynman diagram involving the incoming parton, okay, going to our process of particle production from 1 to n, so 2 incoming particle and n particle production. And the integration over the phase space happen to involve only the momenta of the produced particle. What actually we need there in the cross section is not the scattering amplitude by itself, but as it says, we need the square of the scattering amplitude, and we can compute the square of the scattering amplitude simply by taking the complex conjugation of these diagram and summing of all possible cuts. This is a word that will become more and more used along this lecture, not only in my session but also my colleagues. And the cuts graph are obtained by taking the complex conjugated of the diagram that I've shown here on the top, okay, and by joining the external particle. Okay, so this is the building block that we need in order to compute the amplitude square. And I will leave there on the slides a list of Feynman rules, okay, which we can use to compute the amplitude square summed of the spin of the of the particles involved in the scattering. Let's see an easy example. What I mean, let's describe, for instance, C plus, C minus, 2 mu plus, mu minus in QCD. The Feynman diagram of this process is just one. You have an electron positron, a photon exchanged, and a muon pair produced. This is Q, the transferred momentum, and we define the Mandelstam invariance S like the momentum of the electron plus the positron square plus square, and we have T, which is electron minus mu1 square, equivalently the positron minus the mu1, and then U. P mu minus. And according to the rules that are written on the slides, we can get the sum over the spin of the amplitude exactly by taking the complex conjugated Feynman diagram and joining the external line and paying attention to the fermion line flow. Okay. Okay. To this graphical representation, we would write here 4 pi alpha over s squared, where s technically it's q squared, and then we have to compute these product of trace, the trace on the external fermionic line and the trace on the internal, which we could write like this. Gamma mu slash of the electron gamma nu times the trace of the mu1 minus mu gamma nu. And here, just to be complete, we have the momentum of the electron, the momentum of the positron, sorry, of the mu1, the momentum of the anti-muon, and down here the momentum of the electron. So technically what we are doing in summing over the helicity, over the polarization of the spin of the final states, we are joining this line here, this fermionic line, and using the completeness relation, which relate exactly the spinors wave function to the numerator of the Feynman fermionic propagator, okay, which appear here. And with the regular standard techniques that we should learn at a quantum field theory course, we are able to compute these traces among gamma metrics, and we would arrive to find a result which looks like 8 times 4 pi alpha squared, and then here there is a term which involves the square of the Mandelstam invariant plus other terms which involve the mass of the particle involved, okay, and which for the moment I'm not interested in, so we will forget. So this should be a rather straightforward calculation according regular standard techniques, and we are able to compute so the square amplitudes for this process. I like you to remember this result in particular, so the massless term result, because we will meet in the future in the next hour. Yes, please.
Could you explain why the individual places have only one kind of mass? Why the different masses don't mix in the individual?
Sorry, here this trace it's among the electron-positron mass, and this trace involves only the muon propagator, so technically according to the Feynman rules and the polarization completeness relation, only the mass of the fermion involved in the scattering appears. Does that answer? Okay. Thank you.
So where does the cut come in? I mean, the fact that you've drawn this cut there, how is this?
Is the sum over the LHD here? Okay. It's just yes,
okay.
Yes. Then there is an integration over the phase space. So, but for the moment, let me forgive the integration and let's look just at the amplitude and not at the cross section. Okay. So I will try to introduce now spinor formalism, which is a very powerful technique to handle calculation of object dealing with Lorentz vector, Lorentz tensor, and spinor, namely all what we need to compute scattering amplitudes in quantum field theory. When I think of such a powerful method that I learned after my PhD, it comes to my mind a sentence of Arnold, the mathematician, about powerful techniques, and he is observing another powerful notation rather than technique, a powerful notation, I should say, which is Leibniz notation. Okay, so according to Arnold, the Leibniz notation of the differential symbols is so powerful that it allows who has not understood integration to teach it to who will never understand it. So I really hope, of course, that if Arnold knows the effectiveness of the spinor notation, he doesn't think the same, also because that is not motivating neither for me nor for you to keep going on. And here I have the sentence just. So let's see why how spinors enter quantum field theory and how they become useful for our calculation. So the first time that we heard the word of spinors is when we deal with the Dirac equation. Dirac equation that for massive particle we have, let's say, two versions for spinors related to particles, and version for antiparticle. What we need from the spinors is their representation in the massless case. So when m is equal to 0, these two equations, which are different from particle and antiparticle, therefore the solution of Dirac equation is different among the, in these two cases, becomes technically the same equation. This means that the solutions are degenerate, and we could equivalently describe by the same function both particles and antiparticles. In particular, in the case of massless, in the massless case, it is very useful to introduce the chirality projector, which are defined by the use of gamma 5. Such that we can project out two parts of the spinor wave function. By the action of this projector on the solution of the Dirac equation, and the same for the antiparticle. We will use same kind of equation. Okay. We also have the bar spinors that we need to use in our calculation. This will be U bar and P minus plus on the right, and V bar minus plus P minus plus. Okay, this is the standard notation with the U and V spinors, and now I introduce a kind of a bracket notation, which will be more compact and more useful to proceed along with the calculation. Namely, I define spinor I plus minus, or equivalently Ki plus minus as U plus or equivalently V minus plus, and the other kind of spinors which involve the bar object plus of Ki and V bar minus plus of Ki. This will be probably a notation used by David. Okay, I will use this other notation, really in bracket formalism, and we will. I hope you, by the end of the lecture, will be able to switch from one to another. Okay. So this exhausts the possibility for the four kinds of spinors that we might have. So remember that the U spinor are represented as a column, and the bar spinors as a row. Okay. So as such, we can introduce for the spinors two kinds of products. An inner product and an external product. So, inner product. So we can have two in the inner product. So we can have the angle product, Ij, and the bracket product, Ij. This is the last, which is defined as I minus j plus, and the bracket ij, which is defined as I plus j minus. Okay, these two products are complex numbers. Okay, and they are related. Namely, ij star is the sign of ji product. Not only these, but these products are also antisymmetric. So when we exchange two particles, ij with ji, we get a minus sign both on the angle and on the bracket product. And the product, both for either angle or square among spinors relating to the same momenta ki, vanishes. Okay, so this is a very nice feature that will happen to see the vanishing of terms when we compute scattering amplitudes from different sum of Feynman diagram. So there is a very easy way to see when a term disappears, drops out from our calculation or not. So these are the main. This is the main definition of the internal product, which has said it is a complex number. And let's define now the external product, which instead is a matrix, 4 by 4 matrix. We indeed can form vector momentum by taking the sandwich of gamma matrices onto spinors. Okay, this is a very useful relation. So we can represent the momentum Ki with the spinor product angle I gamma mu square product square spinors I, equivalently represented by the complex conjugated formula. And this expression is valid for massless momentum. We have also this other product, which is P plus Ki slash, or the other product which involves P minus Ki slash, so that we have a representation for K slash in terms of spinors which involve the external product of the spinors. Okay. So thanks to this to definition, we can verify a series of relations, namely that, for instance, the product ij ji is equal to 2 ki dot kj, which we define as ij, namely this is pi plus pj square, ki plus kj squared. In the case of massless momenta case, this happen to involve only the scalar products among the two particles. Another useful relation is the Firth's identity, which can be used for the scalar product of currents among currents, aka gamma mu L, it is 2 times ik Lj, and also charge conjugation, which is realized to a complex conjugation relation among spinors, which flips also the helicities. Okay, these are basic properties that spinors fulfills, and one very notable, I will derive one very notable identity which allows to compactify a lot the expression of Feynman diagram obtained by spinor notation, which is the so-called Shaen identities. Let's assume that we have two massless particles, Ka and Kb, massless. Okay, we know from the algebra of the gamma matrices that K slash Kb slash plus Kb slash Ka slash is equal to 2 Ki dot Kb. And now let's take the sandwich of this expression onto a couple of spinors. Okay, so we consider spinors C. Let me write in this simple notation AB slash D. So we close with a spinor sandwich, one on the left, one on the right, plus C B slash A slash D. This is 2 Ki dot Kb, it's a number, therefore these two spinors, these two test spinors C and D just happen to be joined together. Okay. And now we can use the representation of A slash, okay, in terms of this kind of product. So we will open, we will insert this expression in A and B, and when you use this expression, only one of the two will survive. Only one of the two terms will survive. So we open these strings of this chain of spinors in this way: Ca, AB, BD, plus CB, BA, AD. And we can use for this scalar product here the first dot equation. And we can write this like AB, BA, CD. Okay. So now we can divide out this term BA from here, okay. And here, watch out that there is an AB. So when we cross this guy, we take a sign into account, okay? Because we should first exchange, use the antisymmetry, and then we get a minus sign. And so we end up with the Shaen identities, okay, which I will read from this side, namely that when you have AB CD, this can be written as CB plus AC BD. Okay, so this is the Shaen, the proof of the Shaen identities, and this is probably for the one of you that have not seen the spinor manipulation before, the first step. Okay, it's a first very simple example on how to use properties of gamma matrices, the decomposition, the completeness relation, okay, of K slash decomposed in terms of spinors, really at work. Okay. In general, in an endpoint amplitude, where the sum by momentum conservation, the sum of all momenta vanishes, okay, we can implement the momentum conservation usually in a spinor product, like a sum over I from 1 to n of ji ik equals 0. Okay, so this would be again ki slash, where we run the sum on, and technically, although this sum happen to be on n object, only n minus 2 will give an unvanishing contribution, because I should be different, of course, from j and k. And then I 1 to n. Because when I is either j or k, one of these two products would trivially vanishes by the definition that we gave of the massless spinor product. So when two indices are the same, the spinor product vanishes. Okay. So we have introduced the spinor variable, and we have seen that spinors for the moment have already done a great job for us. Namely, they not only by definition enable us to represent the wave functions of fermions, but they also allow us to represent momenta, okay, of massless particle. The last ingredient that we need to use for computing scattering amplitude is to give a spinorian representation of the polarization of massless vector boson, namely the wave functions of the boson spin 1 particle, massless spin 1 particle, which will be used to represent photon and equivalently gluon polarization in QCD. So we can introduce polarization for massless gauge boson spin 1. There are two states of helicity that we can define for massless particle, either plus or minus helicities. So for a vector boson of momentum k, we need to introduce momentum k squared equals 0, another auxiliary vector, and this in its associated spinors q, whenever there is a representation for a momentum, we can use also the slashed form, so the completeness relation, dotting the momentum into gamma mu. Q minus plus. And in this formula, I had to introduce an auxiliary vector, also matchless. So Q mu, so that its square vanishes, which is called the reference momentum, and which reflects the possibility of a gauge, a particular gauge choice in defining the polarization momentum. All calculation that we do, okay, for a gauge invariant object like three-level amplitudes are, they must be independent on the choice of this reference momentum. But a suitable choice, okay, arbitrary choice, can simplify a lot the analytic calculation that one performs with these spinor variables. Let me just list what are the properties of these definitions, okay, of this polarization vector, and why they are good to represent polarization state. The first thing that we ask for a polarization vector is that it is orthogonal to the momentum k. Scalar, so epsilon dot k must vanish, and indeed that is the case, because when I take k mu, when I dot q minus gamma mu k minus times k mu, these happen to be k slash here, and this is 0 because of Dirac equation, so onto its spinors, okay? And indeed, I could open this just for the sake. I could use again the opening of k slash in terms of its spinors and show that there is at least one spinor product that vanishes. In this case, for the same reason, epsilon is also orthogonal, both polarization is also orthogonal to the reference momentum q, for exactly the Dirac equation, this time acting on the q side of the definition. Also, plus and minus polarization are related by complex conjugation, namely epsilon plus star is epsilon minus. And what we also would like our polarization vector B is that they should be space-like objects. And indeed, if we take the product of epsilon plus times its complex conjugated, which for the properties above would correspond to epsilon minus, by taking the definition I gave you above, we have q gamma mu k over qk and then we have another qk, and here we have the minus spin of q gamma mu k. I can flip the second term in the numerator, q gamma mu k, k gamma mu q over qk qk, and now I can use the Gordon the Fields identity on the numerator. So the minus 1/2 is here. Then the Fields identities would tell me that this scalar product among these two currents is 2 times qk times qk, which cancels exactly the factor in the numerator and gives me minus 1, so that the dot product of epsilon star times epsilon is minus 1. This can be also verified with the minus helicity. And last, so the one before the last property is that these vectors, polarization vectors, are also massless. Namely, we have epsilon plus times epsilon minus star, and in this case it's easy to see that this product vanish. Which is equivalent to epsilon square q gamma mu k over qk squared, and this is 0 because when I apply Fields identities I get qq, it's double 0, so kk, so it's 0 that cannot be more than 0 than this one. Okay. Because we have like spinor product. So the last properties that I would like to show by another calculations did with the spinor product before getting into a real amplitude calculation is the meaning of a choice of a different reference momentum. So what is the role of the reference momentum? What is the difference indeed between polarization state with respect to a same momentum k, but which differ by the choice of the reference momentum? So I like very much, for a reason that I tell you, these simple calculations, which by the way are all contained in Lance-Dixon notes that I mentioned before, lectures, Dixon lectures. If we take a reference momentum, so k, a polarization state plus polarization state with a choice of reference momentum q tilde with respect to a reference momentum q. Okay, then we apply our definitions, and we would have q tilde gamma mu k divided by square root of 2 q tilde k minus q q k divided square root of 2 q k. Okay, so we have to put these two terms on the same denominator. Let's do that. So we have q tilde k, we have square root of 2. We have q tilde k, we have qk. Okay? And now we have to multiply this by, so qk and the numerator, and I do it by flipping. So I write it like minus kq, okay, times the first term, q tilde gamma mu k, and then I have to apply. And then I also flip the sign of this other spinor product, so I have plus k q tilde, and I leave it some space for a second, q gamma k. Okay, since Michael gave me some color, let me use color chalk. So what I've done here is just combining the two terms of a single denominator, okay? And now I want to multiply it by q tilde, okay? Numerator and denominator, q tilde. And here I use, I flip it around to have q tilde q. I don't know if this color is visible to everybody. John Joseph complained. No, it's okay. Should have probably used a brighter one. And very nicely, now I can sandwich together. I can combine together these. There was an equal sign. I can combine together this spinor string and denominator. So I have a global minus sign. And then I can start to combine. Here I have k, then I formed q slash, then I have q tilde slash, then I have gamma mu, and then I have k. And this exhausted this first term. And here there was a minus sign which ended up here in front. And so I can close also this spinor string, q slash gamma mu. Okay. The denominator remain untouched. Q tilde k, qk, q tilde. Okay. Now you see that here I have q slash q tilde slash plus q tilde slash q slash. So I can use the gamma algebra to pull out of this the scalar product, 2 times the scalar product of q dot q tilde. So this whole expression becomes 2 times q dot q tilde. Here what's left in between is just, in both cases, k gamma mu k, gamma mu k, Then I have square root of 2 and all denominator q tilde q tilde qk qk. Now I can open the scalar product between q and q tilde in terms of spinor product. So I write it as a q tilde times q tilde q, and this was the scalar product. That sandwich k gamma mu k, I can use the definition of k mu as a momentum, so it's 2 times k mu momentum, and denominators remain as it was, q tilde qk. Now I'm finished, and the result is qq qk qk sorry, I used the minus sign to write kq, and then I have k mu. So remember that this calculation, I write it, was the result of epsilon plus with a certain reference choice minus the same epsilon with another reference choice. I think that this result is one of the most beautiful equations of quantum field theory, because it expresses many things. Okay? The first property is that it tells us that a different choice of momentum or reference momentum is something proportional to k mu. Okay, so it's a gauge transformation which will be due to momentum conservation or Feynman theorem or gauge invariance will not affect the final result. Namely, what I told you before, no matter what is the choice of the reference momentum, the result will be the same. But there is one more ingredient, which a couple of more ingredients that this equation binds together. The second is an expression of a real massless momentum in terms of 2 other massless momentum, which I didn't tell you before, but they are complex. So namely, if I take a gamma mu sandwich between spinors belonging to the same momentum k, I get 2 times k mu, okay, this definition. And if the momentum is real, then of course this expression between these spinors expression will give me a real object, will give me back a real object. But if I take the spinor sandwich, like in case of the epsilon definition, of a gamma mu with among a spinors q and other spinors belonging to another massless momentum k, this is a complex vector. So this is expression of a real momentum in terms of complex momentum, which it's not really strange, but as we will see, is the basis of all the unitarity and on-shell business. So the possibility to parameterize real massless momentum in terms of complex object. And we will see that we will need to work with complex variable. Okay? And the last equation is that for the one of you that have already more experience in quantum field theory, is that this object here is called soft factors. Okay, so this is the soft factor of particles q, k, q. Okay, which is responsible of several properties, namely the factorization of scattering amplitudes when the momentum in between these two external 1k becomes soft. So just one simple equation derived with the basics of spinor product let us emerge the link that there is between on-shellness, gauge invariance, and factorization, which is probably the main reason why we are all sitting here and why this event has been taking place. By the exploitation of this link between gauge invariance, on-shellness, and the factorization, this I think is the dawn, let's say the dawn of the simplicity, why spinor notation is so powerful. Technically, I don't know, of course with the regular Lorentz notation we could have probably found the same relation, but here it was so simple to derive it. Okay, so let me conclude what I want to say about the spinor notation simply by saying that the spinor formalism, although derived from Dirac equation, it captured the essence of Lorentz group. Okay, for the one of you that even better than me like group theory, spinors enable us to represent a Lorentz group in is 1/2, half group 1/2, representation. And in fact, we were able, just by construction, to represent spinors by themselves for momentum and polarization state for massless boson. Are there questions?
Yes, for epsilon minus is the same, right?
Yes. You would get the complex conjugated of this. In fact, you can always act on an expression with complex conjugation. Then you would get instead of the angle, you would get the square guys. K is Hermitian, so it's real, so it doesn't change. And this you get the minus sign. Thanks for the question. Yes. Okay, I've decided to not introduce mass at all, at least for the moment, in these lectures, because in principle just the calculation gets more involved, but practically nothing changed from the practical point of view. Namely, all massive momenta can be decomposed in terms of massless. A base of massless momenta, so we are in 4 dimensions. Okay, sure, I didn't say that. We are in 4 dimensions, so we need a basis of 4 momenta. We can introduce a basis, and we will, hopefully, at the end of these lectures today, at the end of the morning, we can introduce a basis of 4 massless independent momenta, and we can represent any Lorentz momentum, being it massless or massive, as a combination of massless, and therefore we can apply then the spinor formalism. So although, thanks for the question, the spinor formalism emerged and it is developed in a massless context, it's not a limitation of the calculation. My limitation is due to the space on the blackboard and getting tired to write lengthy expression, which from the technical point of view wouldn't give you any more information than the one I'm trying to give you. Yes.
But this base of massless momenta should also be complex, right?
That's a good question, but we should wait a little bit, as I anticipated. Yes, so since the audience was between less experienced and more experienced people, I tried in this, as said at the beginning, really to start slowly, but as Ioannis was said, a good choice would be a base of massless complex, and this is a first example, a base of massless momenta, a basis of complex momenta, and this is the first example that, for instance, I can represent, if I want, I can represent real momenta as a combination of complex momenta. Let's apply the spinor formalism in real life. with Q and D, going back to our example of before, E plus E minus to mu plus mu minus. So when should I stop? 10:30. 10:30. So let's consider again E plus E minus to mu plus mu minus, and I will use for all calculation all outgoing particle. Okay, so my momentum conservation would be 0 going to P1 plus P2 plus P3 plus P4. Using all outgoing or all ingoing particle helps us with the definition of spinors, but all the other processes can be obtained by crossing, so it's not a problem. So the Feynman diagram for this process is exactly the one that we saw before. The electron, the positron, the momenta are all outgoing, mu minus, mu plus, and then momenta are all outgoing, and I label this particle by 1, 2, 3, and 4 with that momentum conservation. From the standard textbook notation, we would write this current, this Feynman diagram would represent, we start with the current on the left, like U bar 1 and 1, then there is the vertex, minus IA gamma mu, then there is the antispinor, then there is the propagator, photon propagator, G mu over Q square, and then there is the other current, which is a U bar momentum 3 minus IA gamma mu, up, down, up, before. Okay. So this is and Q square is equal S12 equivalent S34. Remember that Sij is the sum of the momentum square. So this is the definition that we would find in the Peskin-Schrader book. The generic amplitudes, okay, for this process, the generic helicity amplitude can be written as m of 4 particles, particle 1 at helicity 1, 2 at helicity 2, 3 at helicity 3, 4 at helicity 4. Let's pull out a coupling constant, and let me call this epsilon directly H1, H2, H3, H4, just to compactify the notation. Okay. So the first, we have 4 choices of helicities. Okay, plus minus, 4 choices to arrange the position of the minus and the plus in this helicity distribution here. This is the general expression, but I have not touched the helicity. So let's start first by computing A 1 plus 2 minus 3 plus 4 minus. Okay. We have to, so we put just plus minus there, and we use the spinor the spinor definition we introduced before and that are listed on that slide, so that this product of currents becomes 1. Then I have I gamma mu. Then I have 2. This I is the complex I, gamma mu. Then I have minus Ig mu nu over S1, 2. And then I have 3 I gamma nu 4. Okay. Now I pull a factor of I in front of my amplitude, and then I can use the first identities, okay, for the scalar product of among these two currents. And the first give me a factor 2, then I have to take 1, 3, 1, 3, then it's an angle product 4, 2. 4, 2. And the denominator, there is S1, 2, which I can write as 1, 2, 2, 1. Okay? Now I multiply numerator and denominator by the same factor 3, 4 angle 3, 4 over 3, 4. Now let's give a look first at this object here, 1, 3 with 3, 4, okay? 1, 3, 3, 4 means 1, 3 momentum K3 slash 4, okay? Now I can use momentum conservation and write a momentum K3 as minus K1 plus K2 plus K4, okay? Momentum conservation. So this I can write it as a minus 1, and then I have 1 slash plus 2 slash plus 4 slash, and this is 4. And now, due to Dirac equation, 1 on 1 vanish, so doesn't contribute. 4 on 4 does not vanish, does not contribute as well. I can write this just as 1, 2 slash 4, which I will open back as 1, 2, 2, 4. Okay? Is it clear, this kind of gymnastic with the spinner? So that plugging back in back in this substitution. So 1, 3 bracket 3, 4, I will substitute by minus 1, 2, 4. My A4, A of plus minus plus minus can be written as minus I, the factor 2 stays there. Here I replace 1, 2, 2, 4. This was 4, 2 and stays here. And 2, 1, 1, 2, 3, 5. Okay? And now I can cancel 1, 2, 2, 1 and a minus sign. And these are exactly the same with the 2, 4, 4, 2. It's the same. So plugging back another minus sign, I get, and my result is 2i 2, 4 square over 1, 2, 3, 4. Okay, so we have computed the helicity amplitudes for the process C plus C minus for this particular choice of helicity. Okay. As we started in this lecture, what we finally need it's the square of the amplitudes. Okay, so since in the helicity formalism the square of the amplitude it's equivalent to the sum of the square of each helicity amplitude, let's compute also the amplitude which is of course a star, okay, a star, and this means we take the same equation, 2i 24 square 1 2 3 4 times the complex conjugated, so we have 2 plus I. Complex conjugation is obtained by changing the angle in bracket and the order of spinor in the argument of the spinor product. 2 1 3 4, and this is 4. Now we can identify now the S invariant Mandelstam product. We have S24 square over S12 times S34. Okay. So in the spinor we have obtained also the amplitude square for this helicity choice. And now we can obtain the other results for the other three helicity choice simply by applying parity and charge conjugation on this result.
Sorry, down there is 4 3.
Pardon?
Square bracket 4 3.
Yes, of course. Sorry. Thank you. I did it on purpose to see whether somebody was watching it. No, it's a joke. Okay. Thank you. So we will use for the other helicity parity, which exchange the helicities, and a charge conjugation which exchange fermion with anti-fermion. So the A4 for the helicity plus minus minus plus can be obtained from the one we computed, plus minus plus minus, exchange a particle 3 with particle 4, and we obtain minus I 2 3 square 1 2 4 3. A4 plus minus it's obtained by the one we computed from parity. So we get minus I 2. Sorry, there is a factor 2 here that I missed. 2 4 squared 1 2 3 4, and last but not least we have A4 minus plus plus minus, which can be obtained by A4 plus minus minus plus, and again parity, and this would be minus I 2 3 square over 1 2 4 3. Okay? Pardon? Sorry?
The numerator of the second one. Yeah.
It's I think it's 2 4, right? Because it's 2 4. No. Sorry, I missed. The second one was minus plus minus plus, and then it's thanks. It was a typo before. So this exhausts the all four possibility of elicit choice that we can have for these amplitudes, and when we square each of them, you see that from this we get. So the numerator is always the same: S12, S43. Okay, because when I take the complex conjugate. S12, S43, S12, S43, S12, S43. And the numerator I can have either S24 like above in this case, or S23, right? So this allows me to compute the square, the sum of the square of the helicity of these mi square, and pulling back the factor, I have a4 e to the 4, so I have 2 times the same kind of object, which amount to be 4 s to 4 square plus s to 3 square over s12 s 3 4, okay, which I can rewrite as 8 4 pi alpha square t square plus u square over s square, since S12 and S34 are the same. Namely, what I've used here is that S12 equals to S34 defined by S, S23 is T, and S24 is U. And this is exactly, okay, the result that we would have obtained, imagine to have obtained it with a regular gamma algebra for the same process which I've shown you at the beginning of the lectures. So you have seen how, without expanding the trace which we had originally for the amplitude square, okay, which would have generated a big intermediate expression, we have obtained an extremely compact representation for the helicity amplitude, and being each helicity an independent object, we could sum them incoherently to get the amplitude square, which after all is what we need for the evaluation of partonic cross-section at hadron colliders. Okay, this was an example of QED, and we will still continue with one more example after the break. Okay, so if there are questions, there are probably still a couple of minutes. Thanks. No, so there is one.
So the last amplitude we could also compute it using this fermi anti-fermi.
Yes.
In principle, you will get something that looks different. That should be the same.
I don't. Why you say different? No, then you. Okay, this was the most easy, but you find exactly the same. Maybe you have to apply some momentum conservation, but the result cannot change. Okay, but that is true. Okay, in spinor, so spinor variables are nice object that keeps results compact. On the other side, there is not a unique representation for an amplitude, okay, to be expressed, and this is one also very important phenomenon that one can use different representation to exploit the parameterization of the amplitude with one kind of spinor product rather than the other, and I think that will be addressed by other speakers, other lecturers along in the next days. Okay, thank you.